All right. So, good morning, everyone. Thank you for showing up early on a Friday. Um Today, like Divya was mentioning, today we'll talk about data analysis methods for climate modeling of extreme weather events. So, this is basically focusing on E3SM simulation and some of the methodologies that we have developed to tackle various challenges around it. So, my name is Ayan Biswas. I'm from Los Alamos National Laboratory, and we will have multiple speakers following my talk. So, their names are also listed in order, and we are happy to present on this spotlight. And if you have any questions, then I think we have a slot for question answers. So yeah, please hold on to your questions. So when we get the chance, and then you can just let us know your questions. And yeah, let's get started then.
In addition to Ayan?
As I was as I was mentioning, so our spotlight is about E3SM. So that is Energy Exascale Earth System Model. That's a big climate simulation, and a large part of it actually is done in Los Alamos National Laboratory. So these workflows or these methodologies that we will talk about on this E3SM simulation, they were developed as part of one of LDRD projects at Los Alamos National Laboratory. The name of the project is In Situ Inference, bringing advanced data science into exascale simulations. So the high-level goal of that project was to perform in situ analysis. So here I don't have to define the word in situ, but in this case, basically we're talking about fitting large-scale statistical models in situ on using E3SM, and there was also another simulation, space weather. And it happens to be last year we talked about the space weather simulation on another spotlight. So this year we are focusing on E3SM. So moving forward, so this is just the introductory part. I'll just take quickly like 5 minutes or so. So the whole breakdown of the talk is like that. First, I introduce the spotlight. Then the next speaker will be Jim Benedict. So he will talk about little bit in detail of how E3SM works, and like why we care about E3SM and what kind of other challenges that might be there for maybe any future opportunities as well. The next speaker will be Shomo Datta. So he will talk about efficient predictive analysis of extreme weather events by in situ data modeling. So in this case, particularly, he will be talking about like an extreme weather event called sudden stratospheric warming. So in this case, basically the wind flow reverses at a certain point in the year and stuff. So Shomo will go into much more detail of that. So basically, he will talk about fitting extreme value modeling in situ, and then how this can be useful like in practice. So the next part of the talk, so Mike Groskopf, he's a statistician at Los Alamos National Laboratory. So he will talk about the distributed Gaussian processes for climate modeling. So in this case, he will talk about a few methods of how we try to fit Gaussian processes, which are generally thought to be very useful, but kind of slow. So how we tackle the problem of scalability and how we used Gaussian processes in situ for E3SM. Next up will be Ruksha Bhaumik. So she will talk about cyclone analysis. And finally, Divya, you already have met Divya. So she will talk about neural networks and how neural networks can help in regression in Gaussian process parameter estimation, and how it can basically, like using some synthetic data as your training, how can that be applied to real data where you can get like orders of magnitude speed up. So with that very high level overview of how we are breaking down our spotlight, I think yeah, it's already time for me to just hand it over to Jim. So yeah, Jim, please go ahead and share your screen, and yeah, take it away.
Okay. I think you have to.
Oh, do I have to unshare first? Okay.
I believe so.
Yes. So now you can try.
Okay. All right. Okay, so yeah, I'm Jim Benedict. I'm from Los Alamos National Lab, a research scientist here. So to begin our spotlight, I'm going to introduce E3SM, which I'll sort of partially introduce. This is a computational framework developed by the US Department of Energy for modeling climate and weather. In this talk, I'll describe how E3SM is constructed, its required computational resources, and its simulation capabilities. I'll also introduce two E3SM weather applications that our team used as part of the larger in situ inferences project. So first, some basic definitions. An Earth system model, sometimes called a climate model, is a numerical representation of Earth's physical, chemical, and biological processes. It's a computer code that estimates the solution to differential equations of fluid motion and thermodynamics to obtain time and space dependent values for physical fields of interest in the Earth system. This can include things like temperature, wind, ocean currents, salinity, soil moisture, vegetation, sea ice extent, glaciers, and many other fields of interest. So the Earth system model being used in one of the Earth system models being used in our study is E3SM. And this program was created by the US Department of Energy about 8 years ago and has since undergone continuous development to add physical process representation and increase spatial resolution. E3SM research focuses on weather and climate impacts on the energy sector. This includes water availability and coastal hazards related to sea level rise, flooding, and extreme weather, which can include hurricanes. Like most climate models, E3SM uses mathematical equations to discretize, that are discretized on a three-dimensional grid mesh that includes grid cells along both the horizontal and vertical axes. You can kind of see this here in the left figure. Grid cells communicate to each other through processes like advection, energy fluxes, and diffusion. Larger processes like mid-latitude storms can span multiple grid cells, and so they're considered resolved on the grid. But we must also represent smaller unresolved processes like individual clouds and ocean eddies through things called parameterizations. And these are statistical theories about how these subgrid scale processes behave. E3SM, shown on the right panel, E3SM is composed of modeling components that each specialize in representing different aspects of the Earth process. And they're all connected through this coupler in the center. So climate models have increasingly become more complex as new physical processes are added and as grid resolutions become finer and finer thanks to increasing computational capabilities. Climate scientists must constantly confront challenges related to the amount of resources needed to produce simulations, as well as the ever-growing amount of data generated by these simulations. So for example, E3SM simulations can require tens of thousands of processors that are run over weeks to months. And they can generate several petabytes of data. So climate simulations are now being run on the Department of Energy's Perlmutter supercomputer, which is shown here. This is the 7th fastest supercomputer in the world as of June. So the in situ inference approach, some applications of which will be described in the following talks, reduces computational burden by performing statistical analyses during the model integration without the explicit need for saving and processing prohibitive amounts of data. Computing power has increased such that global Earth system simulations can now be run at grid resolutions approaching 1 kilometer. This requires grids composed of tens of millions of grid cells. So here on the left panel shows ocean surface currents from an E3SM simulation using a 100-kilometer mesh. In the right-hand panel, the grid mesh resolution along the North American East Coast and up into the far North Atlantic ocean basin has been refined from 100 kilometers down to 10 kilometers. Physical processes that were once unresolved on the coarse mesh can now be partially or fully resolved on the finer mesh, providing new levels of accuracy and detail. Importantly, increasing model resolution is not a panacea, but it generally improves simulations because it reduces our reliance on physical parameterizations. Here's another example. Let me start this. Of an E3SM simulation of sea surface temperature in color and atmospheric moisture and clouds in the white shading. So the simulation's 25-kilometer grid mesh allows hurricanes to be well resolved. Hurricane winds can mix and cool the upper ocean surface, leaving what are called cold wakes that can last for many days. And there are some examples shown here in this simulation. Here's another example. A final example showing sea surface salinity in the Arctic over a 3-year period. Complex processes involving seasonal melting and freezing and coastal mixing can be seen. So when you get this large green shades occurring seasonally, that's indicative of all of the sea ice melt that occurs over the boreal summertime. Okay, let's see. So I'd like to now introduce 2 applications of E3SM to study climate and weather hazards. Previous studies have demonstrated that regional weather extremes can be triggered by other geographically distant anomalous circulation patterns, and sometimes these are termed, quote, modes of variability. One such mode of variability is called sudden stratospheric warming, which Ian introduced. We also call this SSW, in which the strong jet of high-level winds circling the North Pole, this is also sometimes called the polar vortex in the media, breaks down, weakens, and becomes wavier. Cold Arctic air can then move unusually far to the south in the troughs of this now wavy jet stream. And this can produce frigid temperatures and winter storms. And this has occurred several times over the past couple of years, so most people have heard about it. Shomo is going to talk a little bit more about this in the next few presentations. So a second example of how large-scale modes of variability can influence weather extremes across long geographic distances involves a storm pattern in the tropics called the Madden-Julian Oscillation, or MJO. The MJO emerges as a cyclic clustering of thunderstorms along the equator that moves from the Indian Ocean into the West Pacific Ocean. And an MJO phase number is defined based on the longitude of heaviest equatorial rainfall. So in the animation on the left, the MJO is seen as the blue shading moving eastward, with the phase number indicated in the upper right-hand clock. So the phase number is defined here, and it's matching, or it's quantifying the longitude of the maximum of precipitation, which you can see moving eastward here. Previous studies have shown that many aspects of global weather, including monsoon systems, Pacific storms, North American weather patterns, and hurricanes, can change significantly based on this MJO phase number. The figure on the right shows that North Atlantic hurricane activity is strongly influenced by the MJO phase. Knowledge of the MJO phase increases weather forecast skill. So in the forthcoming talk, Rucha will show how the MJO influences North Atlantic hurricane activity in E3SM. So our project is aimed at developing in-situ inference methods, or the application of probabilistic statistical modeling applied during a climate simulation. This in-situ analysis can identify critical connections between hazardous weather events and their precursor conditions, and it can reduce the need to store and process the full model output. These hazardous weather events significantly impact utility infrastructure and human health. So this figure on the left is from a 2021 Texas cold wave in which the power grid had numerous failures. And on the right is the 2012 Superstorm Sandy flooding, which was caused by a remnant hurricane. Okay, so in this talk, we have seen that the Department of Energy's Earth System model, called E3SM, is capable of simulating climate and weather. events that can adversely impact society and energy infrastructure. We've also seen that computational resource and data management burden increase in step with ongoing model grid refinement. However, in situ inference methods, some of which will be described in more detail in the next few presentations, can be used to facilitate climate model analysis and reduce computational burden. So I think that's it for me. So next is going to be Shomo, and he's going to talk more about the sudden stratospheric warmings.
So thanks, Jim. Can you see my PowerPoint?
Yes.
Okay, thanks. So thanks for the nice introduction of E3SM and also describing the problem. So the title for my talk is Efficient Predictive Analytics of Extreme Weather Events via In Situ Data Modeling. So my name is Shomo Datto, and currently I'm an assistant professor at IIT Kanpur, India. But part of the work when I did it, I was at Los Alamos and I was in the information sciences group. So if we talk about in situ climate modeling, then for our particular example, we are trying to detect an event called SSW, sudden stratospheric warming, using DOE's coupled Earth system simulation energy exascale Earth system model, E3SM. So for this, we have first built an efficient in situ infrastructure so that we can do in situ analysis using E3SM. Then we deployed a robust in situ SSW detection algorithm. And then we collected some data during the in situ run, and then used that to study the impact of SSW on surface temperature from the in situ generated data. So the way we define SSW is that it is a major midwinter warming that occurs when the zonal winds at 60° north and 10 hectopascal become easterly during winter, defined here as within the month of November and March. So this is basically an abrupt warming event in the polar stratosphere. And as you can see on the right-hand image, I'm showing a plot where the x-axis indicates the day of the year, and then the y-axis indicates the value of this measure. And we see that highlighted by red, a sequence of days which are more than 10 days, and we have the value of this measure negative. So that's an event that is SSW, because that is satisfying the this particular definition of SSW. And understanding about these SSW events are extremely critical because this has impact on energy security, as these events can lead to extremely cold air outbreak in United States, specifically on the surface level. And these are popularly known as polar vortex events in media. So why do we need in situ analysis for this particular case? So Earth system simulation data is too large, as Jim already mentioned, and there is a IO bottleneck. So we need to perform almost real-time analysis to be able to tap into the large-scale data that is getting generated by E3SM, and offline analysis will not scale. And then one may ask that we can just store the relevant variables that is needed. But there are problems to do that because it will limit the exploratory capabilities significantly. And then the other problem is that there are multiple definitions exist in the literature for detecting SSW. And then they require, like, different definitions require different pieces of the data. And then if you limit your variables, then that also limits the capabilities. And then we also want to study the linkages of SSW using a 3D spatiotemporal data set, which is going to be too large to store. So we really need in situ analysis for this task. The new capabilities that we have developed in this particular piece of research is that we have developed a new in situ pathway that uses Julia as the coupled programming language. So essentially you can write Julia code. Julia is a Python-like language, but then it is high performant. So you can write a Julia script, and then you can run the script using our in situ interface. Then we have used the interface to study, to perform SSW guided adaptive in situ data modeling of surface temperature data. And then we have done some post-hoc analysis to show what kind of results we are getting out, and then how we are able to measure the impact of SSW on predicting surface temperature. So a little bit about our modeling. So we have multiple modules in SSW as shown on the right-hand image, and we are only focused on the atmosphere part of the module. And the way we did our in situ integration is shown here. So atmosphere module has internally multiple modules again. So you have dynamics grid, you have physics grid, you have control module, and then there are several more others. So we defined our in situ code, the function that does in situ inference in the dynamics grid. And then essentially we pass the data from the Fortran through a C pointer, and it essentially passes the data in a Julia environment. And in that Julia environment, that Julia script that the user has defined for performing analysis can be run. So this essentially taps into the atmosphere simulation data. The data distribution is spatially contiguous in this case. And then we are effectively able to access at a desired time frequency how we want to access the data in situ. A brief overview, I don't want to go into the detail, but then this is essentially showing that we just have one line of code here in a function in E3SM, and this is the entry point function for us. So this is essentially showing that we have minimal modification in the code. And this falls under the category of direct in situ integration, where the simulation and the in situ code is running at the same, using the same resources. So the simulation sort of waiting when the in situ code is running. And we are using the same E3SM MPI communicator. So in Julia module, you can write distributed code as well. And we need distributed communication to have this SSW measured. And then also, so this is again showing a very brief highlight of the Julia, of the in situ interface, the function that we are calling from the last slide. So we start the Julia process, and then we have a function called streaming. So the streaming is essentially a Julia function, and we are calling it from the Fortran interface, and we are passing the essential data array that are needed, and also the MPI communicator. And then at the end of the process, we exit from the Julia environment. So it's a simple skeletal structure that shows how the interface is working. Now, our algorithm flow is something shown as this image. So E3SM is running, and then you have Fortran. The data gets passed through a C interface internally, and then now you are in the Julia environment. So in the Julia environment, the way we are working to have this SSW detected in situ is that this algorithm requires you to check the data per day. So first we check whether the current time step is end of a day or not. If it is an end of a day, then we apply a function that measures the SSW, the definition that I have showed. We essentially implemented that in Julia. And then it essentially maintains two set of distribution models because we want to model the surface temperature value. So if we detect SSW, then we have a specific set of distribution model where the parameter gets updated using the surface temperature values. And then if we see that this particular end of the day is not an SSW event, then we have another set of distribution model that gets updated. So we essentially keep track of two set of distribution models, and then we continue to update depending on this flowchart, whether you are detecting SSW or not. And then we keep storing the distribution parameters as an output for the post-hoc analysis. So a bit about the specific distribution model. So since we are modeling extreme value distributions, in this case, say maximum or minimum temperature values, so we are using a distribution called Gumbel distribution that allows you to model such extreme value distributions. And I'm just showing the equation here. And this has two parameters that needs to be estimated. And we use a variational inference algorithm to implement the parameters in situ. And on the right-hand plot, it shows that how, if you change the value of mu or the beta parameter, then how the plot, how the distribution shape and the skewness changes essentially. So a little bit about the validation and the results that we have obtained. So to validate this algorithm, we first ran the E3SM simulation for 85 years. So we started from the year 2015, and then we simulated up to 2100. So we collected the data, and then we found that there are 5 of those 85 years where a valid SSW event has been detected. And on the right, I'm just showing one example that satisfies our specific definition of SSW. And this is from the year 2098. So like towards the end of our simulation run, we found 1 year, and then there are multiple other years that has SSW. And in this plot, we are showing how the distribution parameters that we have stored, essentially the Gumbel distribution models, can be used to infer that whether certain part of United States will have colder temperature and how it varies non-SSW with this, or how it compares the non-SSW version of the data with respect to the with the post-SSW version. So on the left, I'm showing that these are the probabilities of observing extremely low temperatures in the continental US. And in this case specifically, we measured that less than 10 Kelvin below the seasonal mean. And you can see that the highlighted red part, the value of the probabilities are quite high. So it's extremely cold temperatures can happen in this region compared to the non-SSW year. So if you have an SSW year, then the winter can be extremely cold for a set of days. And on the right-hand image, I'm showing the non-SSW versus post-SSW image. Here, the quantity we are showing are the uncertainty of the distribution models that we have estimated. So you can see that for the post-SSW, the uncertainty is high. And that is sort of reflecting that since the SSW is a rarer event in general, so we didn't have enough data. So expectedly, the uncertainty is high because it's a rarer event. So you have less number of data points. But as you keep running the simulation and then gather more data, then you will have much more higher confidence in the prediction. And finally, some result from the in situ run. So we implemented the complete pipeline that I have shown in situ, and then we have deployed that using an E3SM test case, which is a realization of the shared socioeconomic pathway 585 scenario. And in this particular in situ run, we simulated 3 months of the three simulated months. And so we stored the GeV extreme value distribution parameter as outputs. And this particular simulation case was run on 84 computing nodes, and which spanned across more than 3,000 processors. And we found that the in situ algorithm only took about 10% additional time to the simulation time. So not much extra overhead, but then we are able to capture the distribution models in an incremental fashion. And on the right, I'm showing the same plot. In this case, we did not detect an SSW because the days spanned were not 10 consecutive days. So that has to be a criteria to meet the SSW definition. So this was not an SSW, but then this shows the technique that we can apply our technique in situ. And then here I'm showing one image that shows the predicted mean surface temperature for the continental US that was inferred from the distribution parameters that we have estimated in situ. So in summary, we demonstrate a novel in situ visual analysis pathway for DOE's climate simulation E3SM. We design an in situ predictive algorithm to study the extreme weather event SSW and its impact on surface temperature variations for continental USA. And we show the practicality of our visual analysis method by running the pipeline in situ and showing that it takes only additional 10% computational time. So I'd like to acknowledge the funding resources, and here are a few references. So we had a paper on this, and which won the best paper award at last year's ISAV. And with that, I conclude my talk. And next will be Rupsha talking about cyclones. Thanks.
Okay, thank you, Shomo. Rupsha, you're up next.
Yes.
Was the order changed, or was
sorry, that was my mistake. So
is it
Mike,
up
please.
next?
Yeah. Sorry about that. No, Mike, please go ahead.
Okay.
Okay, thank you, Shomo. Sorry, I just was confused there for a second.
No, sorry about that. It was my mistake.
Let me pop my slides up here, so I hope everyone can see my slides. So I'm going to be talking about distributed Gaussian processes for spatial climate modeling in the same context of in situ inference with E3SM. So as has been highlighted already by some of the others, extreme events can be really important and really important to national security. Things like polar vortices, high wind events, these things can be very costly, can impact people's lives, and can generally be sort of large large impact events that we want to be able to use our impressive simulation codes like E3SM to understand the processes of, to be able to forecast, to be able to understand relationships between them and other atmospheric processes, so that we can better prepare, and better adapt to extreme events, especially in the world of a changing climate with more extreme events. But these big simulations, as Jim mentioned, are getting bigger and bigger. They're getting finer resolution. They're generating much more data. And instead of the computation being a bottleneck, the data storage and communication is really the bottleneck. So, we can generate huge amounts of data through computation, but then only pass a limited amount, from computation to node memory, and even less from off of node, and even much less back to hard drive storage, back to writing out, so that data analysis can be done later. And so, if we're generating all this data, but we can't actually get to it, how useful is it? Well, to get around that, as Shomo talked about a bit, we're trying to move our inference in situ. We want to be able to do our inference in line while a simulation is running. So instead of writing out and doing everything post-hoc, we want to do the inference in the computation, and then get the inferred model out at the end. So acting as sort of a summary of whatever aspect of the detailed dynamics that we're trying to look into. And so you may be then asking, what type of inference are we looking into? Well, as Shomo just talked about, one of the things we care about is modeling extreme value distributions. So Shomo did pointwise extreme value modeling. So for each location in space, fitting an independent Gumbel model, fitting the parameters of that. But we expect there to be, spatially contiguous structure in extreme value models. We would expect in some regions of, say, the plains, that the probability of extreme temperatures or extreme winds or extreme precipitation events to be similar if you go 50 miles down the road. Now, this isn't always the case because of geographic structures, things like mountains and everything, or coasts. You may not expect this to be spatially contiguous everywhere, but in general, we would like to be able to leverage the fact that we have spatial structure to these extreme value models. And so, we want to build these parameters not just independent, but as functions of the underlying spatial surface, and potentially other things, maybe including altitude or other structures to handle the other processes involved. And so, if we want to do spatial inference, the most common method, one of the most common methods for doing spatial inference with trying to capture uncertainty in the underlying spatial fields that we're inferring, or underlying functions that we're inferring, is using Gaussian processes. So you say, those parameters are a function of something, say space, and we're going to put a prior distribution on the functions, and then we're going to use data to update our information. We're going to put a Bayesian prior on the function. We're going to get data. We're going to do Gaussian conditioning. We're going to do Bayes rule, and now we'll get new Gaussian means and Gaussian covariances to describe the mean process and the uncertainty. And so this plot here is a simple 1D Gaussian process, just showing how you may start with a prior that just describes random functions, but then when you condition on a few points, sorry, I keep clicking and it moves me forward. When you condition on a few points, then you now know where those function values go through, but you still have a lot of uncertainty in where the random functions may go through around them. And a lot, you have them concentrated in some areas that respect the, say, smoothness of the expected types of functions. But then there's still uncertainty because other versions of functions can get through all those points. So Gaussian processes are very flexible. They're very powerful tools for doing spatial field inference, for estimating unknown functions, and importantly, getting uncertainty on those unknown functions. Unfortunately, they don't deal well when you have lots of data. When we have these big, this big spatial field in the simulation that has very detailed resolution, we can't build some of the aspects of the Gaussian process to deal with all the data. The inverting covariance matrices in the Gaussian process update equations takes scales as the number of data points cubed, and storage-wise scales as number of data points squared. And that's just not a feasible computation when n gets big, when the number of data points is big. So there's been substantial work across many areas in trying to identify ways to sparsify Gaussian processes, or to make Gaussian processes tractable for big data. And inducing point methods are one of the most common approaches to this. Inducing point methods basically say, if you may have n data points, you may have a huge amount of data, but you probably don't need to use every one of those points to describe the surface. There's probably some shared redundant information. And that if you can use a smaller number of optimized representative points or inducing points, you can get a good approximation to that full Gaussian process with order m cubed time instead of n cubed time. So for our in situ inference needs, we need the Gaussian processes to be scalable. We need them to be able to be distributed into contiguous blocks so that we can do our inference on local structures within these big distributed computations. And we need them to be able to plug into the existing simulations without degrading the performance of the simulation. We, as Shomo said in his, he was seeing, getting like 10% impact on some of the streaming VI aspects. And we need the Gaussian processes to be similar. If the Gaussian process slows the computation down too much, it's just not reasonable to include. As was mentioned a bit, we've built this ability to do in situ inference in E3SM, and as part of that, we built a Julia package to do in hierarchical sparse Gaussian processes. This package interfaces with the Fortran code, as Shomo was talking about, to communicate state information and do our in situ inference. And so the higher level goal, just to restate what Shomo had said there a little bit, is that E3SM, as it runs each MPI rank, launches a Julia instance, its own Julia instance. And then as the system evolves, it communicates data to that Julia instance. Julia can then do the inference, say updating a spatial Gaussian process model, and then give control back to the code and move forward. And so we have this, so each rank has a Julia instance sitting alongside it, and that just gets pointers to data communicated to it, does inference on that data, and then continues the simulation. And so this is a case just fitting. I have just a very coarse sparse Gaussian process to all the data, but what we'd really be doing here is that this whole data would be partitioned up into small chunks, and we'd be fitting sparse Gaussian processes to each chunk. How many chunks? A lot of chunks. In the standard resolution, the 1 degree resolution E3SM model, this is not the big, order 1 kilometer simulation that Jim talked about in his talk, but this is a more standard one that we could run on the Grizzly cluster at Los Alamos. We have 2,700 partitions of the Earth on this squared cube sort of distribution, and so you can see that each color represents its own partition. So you can kind of get an idea that there are many small partitions here, and each partition gets its own MPI rank. And as mentioned, as Shomo mentioned, we're not going to have the Julia do the distributed, the organization of the distribution. We want to be able to let Julia plug into E3SM's distribution of the data so that there's not complex communication going on with different levels of MPI happening. So we've been able to take these spatial GPs, and we've been able to fit them in situ with mostly so far with fitting independent sparse Gaussian processes across ranks in situ. And so here is one instance where we have at one fixed time, the upper atmosphere temperature on the left from E3SM, and in situ Gaussian process predictions on the right. You can see that the in situ sparse Gaussian processes are able to capture the spatial structure of the temperature in great detail, very accurately. With 5 inducing points, as is the image in the upper right, you get around half a degree RMSE, and a little worse if you go to just 2 inducing points, but then you sort of saturate how much the GPs are getting, where when going up to 10 gives you very little further increase in predictive capability and starts to increase the time. And so I talked about we need to do this without having big impact. Well, the time to fit there is 3 or 4 seconds, and one time step of E3SM is roughly a little over 1 second. So running this every time, fitting in a sparse Gaussian process every time step would increase the full computation time by 4.5 times. But on the other hand, we want to do things like extreme value modeling or just fitting surfaces at different intervals. We don't need to fit every time. And so even if we're just dealing with fitting something with daily extremes, where we're updating the sparse Gaussian process each day, that's 48 time steps on standard resolution. So it'd only be a 7% impact rather than a 7% impact rather than a 4,600% impact. So I said we've right now been doing, so the result I have here is with independent, so each node fits an independent Gaussian process that doesn't have any information of what's happening on other nodes, but we have some approaches that we've been working on to try to improve smoothness and get communication across nodes so that longer scale structure can be captured. One of which is a hierarchical approach, where we have a central node that fits a global structure to all the data, communicating, doing mini batch communication to across nodes to update a global model that's then broadcast out to all the local nodes, that gives an idea of the large scale smoothness in fitting the local models. And Kellen Rumsey had a paper at the SPIE Applications of Machine Learning conference on this a couple of months ago. We also have a decentralized PSVGP, or partition sparse variational Gaussian process approach, that we've worked on, in which the basic idea is we want to get implicit smoothness by having each partition not just predict its data, but predict its neighbor's data, so that neighboring Gaussian processes have to predict each other's data, and ideally getting then implicit smoothness by the fact that they have to both be good at predicting across the boundary. This is all done through local point-to-point communication, which allows it to scale much better than a hierarchical approach with a central bottleneck. We have a paper in review at AI Stat about this, but this is something we find to be really interesting and useful. So I'll wrap up here so we can get to Rupsha, but I just wanted to summarize by saying we have this ability to do distributed sparse Gaussian processes for in situ inference in E3SM, including fitting spatial extreme value models like the spatial Gumbel model, or in principle, the spatial GEV model, though there's parameter support issues on the GEV model. So the Gumbel is the one we have working at the moment. But yeah, I think I should wrap up here and be able to pass off to Rupsha. So thank you for your time.
Wonderful. Thank you so much, Mike. Rupsha, let's keep this going so that we can get through in our allotted time.
Sure. So I'll just quickly share my screen. Can you see it full screen?
Yes.
Okay. Hi everyone. My name is Rupsha Bhaumik, and today I'm going to talk about how Median-Julian oscillation altered the tropical cyclone occurrence and their intensity over the North Atlantic Ocean basin. So here I'm using the E3. So this is mainly an application of E3SM based work. So moving on. So like I said, this is an application of E3SM based work. Here we are validating the performance of E3SM in feature detection of tropical cyclones over the North Atlantic. And we are focusing on main cyclone season, which span from June to November each year, and then we are comparing the performance of E3SM with the observation, and we are also looking at how the base environment or the physical environment changes that contribute to the tropical cyclone biases. And then moving on, we also computed the tropical cyclone occurrence alteration in different MGO phases. So MGO is that teleconnection process that Jim introduced in his talk, and we are also going to look at that how the physical environment differs in different MGO phases that can ultimately influence the tropical cyclone occurrences. So this work is mainly based on feature detection of tropical cyclone, and for feature detection I'm using a Tempest Extreme algorithm. So this is our first result where we detected the tropical cyclones using the Tempest Extreme, and we compare the result between the E3SM and the observation. And our data spans from 1980 to 2015. So if you can see, in general, E3SM produces or it detected much higher number of tropical cyclones compared to the observation, and the wind speed of those cyclones detected by the E3SM is also higher than the observation. So if you can see this red region, this part is called the main development region, stated in different way that most of the cyclone over the North Atlantic developed over this particular area. And if you can see that in E3SM, there are a higher number of cyclones generated over the NDR region compared to the observation. So E3SM basically, but E3SM actually underestimates cyclone occurrence over the Gulf of Mexico and the Florida coast. But it overestimates cyclone occurrences near the East North Atlantic compared to the observation, where observation actually overestimates cyclones over the Gulf of Mexico, but it underestimates the cyclone occurrence near the Western Africa coast. So the main reason of this difference tropical cyclone statistics is based on how the physical environment, both in model and observation, behave. So that actually alters the cyclone occurrences. Moving on, this is another statistic. So here I am showing the tropical cyclone track density spatial distribution, where the blue color means that higher number of cyclone occurrence compared to in the yellow or in the lighter green shade region, where the lower number of cyclone occurrence. Sorry. So here I'm also comparing the results between the E3SM and the observation. So you can see that for the E3SM, the subtropical North Atlantic experiences highest number of simulated tropical cyclones, but for the observations, Northwestern Atlantic experience the highest number of cyclones. But in general, if you can see the results, most of the cyclone, so the highest cyclone occurrence actually happen over the subtropical Atlantic over this part. So this is mainly because this portion of North Atlantic receives the Gulf Stream, and Gulf Stream provided the warmer sea surface temperature, and this part of the region also experienced the westerly trade wind. So, and these two are the major contributing factor for more tropical cyclone generation. So this is why this portion of North Atlantic in general receives higher number of cyclones rather than the rest part of the Atlantic. This plot is showing the tropical cyclone strength or intensity spatial distribution, where in both of the plots, the darker blue shades mean the cyclones are much stronger, and the lighter blue shades mean the cyclones are weaker. So in general, E3SM cyclones are much stronger than the observation, because you can see that E3SM cyclone has high intensity until 55 meter per wind 55 meter per second wind speed, compared to in observation, where the highest where the strongest cyclones has the 40 meter per second wind speed. And so if you can see the spatial distribution, the simulated or the E3SMTC tropical cyclones have the maximum wind speed near the northwestern Atlantic and the Florida coast, which is over here. But in comparison, for the observation, the tropical cyclones has actually the most strong tropical cyclones occur near the Florida coast, and it's again the physical and it mostly depends on how the physical environment in this in the simulation and in the observation behave, that can actually control the tropical cyclone occurrence and tropical cyclone intensity. And we are moving on to that part later. So this is another tropical cyclone intensity metric. It is called the accumulated cyclone energy. So or ACE. So ACE is a cumulative sum of tropical cyclone wind magnitude across all the storms. So in the so over the top panel, the bar plot is showing the cumulative ACE of on seasonal basis. So each bar is representing the cumulative ACE of each TC summed over the season, and on the bottom panel, the bar plot is showing the observational tropical cyclones ACE. So in general, you can see that the simulated or the E3SM tropical cyclones ACE is much higher than the observation, but the observation tropical cyclone ACE has the actually experience a higher fluctuation over the time compared to the E3SM. And on the top panel, the right plot is showing that the maximum ACE distribution, where so for E3SM, the strongest tropical cyclone or the strongest ACE actually happened over the Caribbean Sea region. So the Caribbean Sea is also another big hurricane developing region, and for the observation, the maximum ACE is actually, you can see over the North Carolina Carolina coast. So this is how the climatology of tropical cyclone over the North Atlantic actually differs between the E3SM and the observation. But in general, observation tropical cyclones and its strength is much lower compared to the simulation. So now moving on to actually showcasing that why the tropical cyclone statistics differ the way, and the answer is that that is base physical environment, because the base physical environment actually differs in the model and in the simulation, and that actually mainly causes the different tropical cyclone statistics. So in this plot, so in the A and B, I am showing the moisture distribution for E3SM and for observation. And if you can see that for the E3SM, the Florida coast or the Gulf of Mexico experience a dry environment compared to the observation. And if and this SST plot, so in the C panel, we are showing the sea surface temperature mean seasonal climatology. So if you can see, so in that SST composite plot, if you can see this part, which is the Gulf of Mexico, you can see that there is a cold bias of sea surface temperature, and over the East Atlantic there is a warm bias of sea surface temperature. So this, so if you can see like this tree plot, it actually answers the tropical cyclone climatology of the E3SM. That so it means that cold sea surface temperature biases and the dry moisture distribution over the Gulf of Mexico actually causes less number of cyclone occurrences over the Gulf of Mexico for the E3SM. And also this is a mean seasonal climatology. So I compute the climatology from June to November for each variable from 1980 to 2015 to match the tropical cyclone season. Moving on from the general tropical cyclone statistics to see that how the MJO phases influence the tropical cyclone occurrence. So as Jim said that MGO is a teleconnection pattern that spans over the North Atlantic and the Pacific. But in E3SM, MGO amplitude and its related influence and the weather is relatively weak over the North Atlantic compared to the observation. So these two composite plots showing how the MGO phases and the amplitude looks like in its different phases. So if you can see that the E3SM MGO composite, it is overall in E3SM, MGO is overall very weak compared to the observation. Especially if you see over the North Atlantic. So this part is the North Atlantic. In this portion, MGO even don't have any like showing amplitude compared to the observation. So this is one of the findings that ETSM actually the representation of MGO phases in ETSM is relatively weak compared to the observation. So now moving on to the tropical cyclone statistics in different MGO phases. So here MGO is actually have 8 different phases, but here I'm showing the two main opposing phases and how the cyclones differs in those two opposing phases. So if you can see that in MGO phase 4 or this is called the easterly phase. In easterly phase, the number of cyclone occurrences is very lower than the MGO phase 8 or on the westerly phase. So cyclone generation mainly favors the cyclonic low level relative vorticity. And in the easterly phase, so the easterly phase actually mainly characterized by the anticyclonic wind anomalies. Compared to that, in the westerly phase, it has the favorable cyclonic wind anomalies, and this is one of the main reasons that easterly phase has a lesser number of cyclones compared to the westerly phase. This plot is showing how, the physical environment or the mean state biases in different MGO phases that contribute to the tropical cyclone biases in those MGO phases. So here I'm showing the moisture distribution in easterly MGO phase. So this plot is actually showing the difference between E3SM and the observation, and so the green color means that E3SM overestimates the moisture distribution, and the brown means that E3SM underestimates it. And where the difference is significant, we define that using these dots. So if you can compare the results between the easterly phase or the MGO phase 4 and MGO phase 8, in the MGO phase 4, the environment is comparatively dry, or you can see that especially over the Gulf of Mexico, there is a less moisture compared to the and also overall on the North Atlantic, it's comparatively dry compared to the phase 8. So it's mainly that anticyclonic wind anomalies along with the low moisture in phase 4 ultimately contributed lesser number of cyclone occurrences in the MGO phase 4. So this work completely has been done over the offline mode, but we can apply the MGO phase detection and the tropical cyclone detection into the in situ framework. So this is the application that we can apply into the so that is the main application of feature detection, that we can apply that entire feature detection process of tropical cyclone into the in situ environment. In a nutshell, so from this work we identified that ECSM overestimates tropical cyclone near the subtropical Atlantic, but it underestimates tropical cyclones over the Gulf of Mexico. And so sea surface temperature and moisture biases are the mainly contributing factor for this altering tropical cyclone climatology biases for the ECSM. And then observation so comparing with the ECSM, observation underestimates tropical cyclones over the subtropical North Atlantic, and it's mainly due to the dry moisture biases. And for the MGO phases, MGO amplitude is relatively weak in ECSM, but overall we can see the eastward propagation, and we can see the correct eastward propagation. And the next, so when we see the differing cyclone occurrences in different MJO phases is mainly due to the wind anomalies and the wind direction and the moisture distribution. So at the end, so this work has two future research options. We use Tempest Extreme for future detection of tropical cyclone, but we also use Tempest Extreme to detect the tropical cyclone climatology, including the ACE. So we can also use the Tempest Extreme to detect tropical cyclone related precipitation and tropical cyclone related extreme precipitation for both simulated and observed data. So this is one of the main future research plan that we want to accomplish related to the future detection of tropical cyclone. Thank you.
Okay. Wonderful. Thank you so much, Rupsha.
Thank you.
All right, so I know there's a bunch of questions that are coming up in Slido and stuff, but we are very quickly running out of time, so we're going to answer questions. I have one more talk to present today. All right, thank you. So for my portion of the talk today, I'll be talking about how we use neural networks for data regression and climate data. So as many of my colleagues have mentioned today before me, we have a lot of E3SM data, climate data, and it's a coupled system. And even if we just look at one component of that coupled system, say the atmospheric component, we predict that we'll have about 18 gigabytes of data per snapshot of this one component of E3SM. And if we're looking at, say, every 6 hours, saving that much data, pretty soon, if we're looking at something like that's over 50 or 100 years, which is pretty typical for looking at macro events in climate, we'll have petabytes of data. And we know that this is really impractical and essentially impossible to save this much data for post hoc analysis. So in this project, we looked at other ways to represent this massive amount of data through data regression and data compression methods. So one solution that we came up with was to fit Gaussian processes to portions of the data and therefore represent the data as a Gaussian process. And Mike talked about kind of the different ways to do that and how useful that is. However, traditional Gaussian process estimation for really large data uses things like maximum likelihood estimation, and this is quite slow. And so what we did in this work was that we presented a different method that used convolutional neural networks to predict the parameters of this Gaussian process. The network is trained offline with synthetic data that really has nothing to do with the climate data that we're looking at, other than kind of defining the range of values that we're interested in. And then we use the network to identify Gaussian process hyperparameters in an online setting on the E3SM data that we care about. So we looked at two different E3SM data sets, the two ones that I'm presenting here. It's the temperature at 1 millibar and the temperature at 0.1 millibar. And you can see that these two data sets have very different types of features. You have larger low frequency features as well as smaller high frequency features. And really the goal was to train a neural network so that we can estimate both types of features and pretty much everything in between. And so we know that we want the Gaussian process to model the 2D spatial temperature field as a function of the longitude and the latitude of the datum. And so by prescribing a zero mean in our Gaussian process model, we focus on capturing the spatial variation of the temperature field through the covariance function. And we did that by understanding the anisotropic squared exponential kernel, which is the function that I've shown there. And there's three main parameters here that we care about. We care about the sigma, the L1, and the L2 parameters. And this set of parameters form the set of hyperparameters that we want to predict using our neural network. Really, the idea is if we can do this really fast, then we can determine our Gaussian process fitting really fast and therefore make this all feasible within an in situ environment. So what we did is we wanted to look at a range of different values for both the L1 and L2, and that corresponds to the latitude and longitude, and therefore capture a wide variety of different spatial features to be able to train our model. And so we generated 32 by 32 samples, just kind of picked a reasonable size, of synthetic data at various combinations of these three sigma, L1, and L2 parameters to train our neural network. And we know that some combinations have smaller high-frequency features, where others have larger low-frequency features. And so we identified a pretty reasonable range for a hyperparameter set to train over. But we realized as we trained our model and applied it to actual data that values slightly outside of this range work pretty well too. And so the idea is we take our simulation data, crop it up into smaller chunks that kind of are closer to that 32 by 32 range, and then we pass that through our neural network, predict the hyperparameters for that area, and therefore now we can represent parts of our data and essentially fit parts of our data into different Gaussian process functions. And so we trained a neural network, and our neural network format is shown there below. We have 3 different convolutional layers, 3 max-pull layers with some batch normalization, flattened, dense, and a dropout layer complete our network. And so if we look at some of the results of our convolutional neural network versus the maximum likelihood estimation, kind of the traditional gold standard for Gaussian process fitting, we see that for the 3 different parameters, the hyperparameters that I talked about, the black lines represent the 1-to-1 fit, so like a perfect fit. And there's 400 orange and 400 blue points that correspond to the 400 samples from each of our 2 data sets from the E3SM data set. So you see that the longitude and the sigma data set fit pretty well on that 1-to-1 line. So we see that those correspond really well. So the predicted values from our neural network correspond pretty well to the gold standard of the maximum likelihood estimation. The latitude values also fit pretty well, but they're slightly offset, and we believe that corresponds to the smaller range of values that we used for training our latitude versus the other parameters. But as I go through the rest of the talk, you'll see that really none of these small variations really mattered at the end, because we saw that the results between the neural network and the MLE in other ways were pretty much spot on. We also looked at a few different statistical metrics. So we looked at the Hellinger distance, the normalized symmetric KL divergence, and the mean prediction relative difference metrics. And all of these metrics, both for the mean and the median for the 2 different data sets that we looked at, showed that the CNL-based parameters and the MLE parameters produced similar Gaussian process distributions and predictions. Finally, we compared the conditional mean prediction for the MLE versus the CNN. So we looked at the reconstruction using the CNN compared to the MLE, using the parameters, the sigma, L1, and L2 parameters defined by the CNN. And then we mapped the absolute error difference between these 2 prediction sets. And we saw that the errors were orders of magnitude smaller than the data itself, indicating that really there's no practical difference using one method over the other. And finally, the thing that we really cared about is the CNN able to predict these values much faster than the MLE. And yes, if we looked at the mean runtimes for the 400 samples for each of the data sets, we saw that the CNN is indeed able to predict these hyperparametric values about 4 orders of magnitude faster than the MLE. So really encouraging information to really say that we can now go and implement this in an in situ way and make this feasible in an in situ way. So all of this work was published last year at the IEEE Big Data Conference, at the IEEE International Workshop on Big Spatial Data. So if you're interested in more details, go ahead and refer to that reference there for that. And now I can open it up for questions, both for myself as well as my other colleagues who participated in this application spotlight with me. All right, thank you so much for your time. Oh, and a big round of applause for all my collaborators who couldn't be here. A thank you to them for presenting their work as well. All right, any questions? I know we had a couple of questions on Slido. So one of the questions was regarding the work of in situ, and now I might have lost these questions. So, Ayan, I think you were answering some of the questions. Do you want to maybe present that to the group here?
Yeah, but can you hear me?
Yes, we can hear you.
Okay. Yeah, so we had a few questions on Slido. So while the audience present they're coming up with their questions, I can just quickly recap those questions. So the first question was, so this was a question about E3SM. How do you initialize the state of the simulation prediction model? Do you record the different parameter values for each grid cell on Earth for initializing the simulation? Do we have probes with the required resolution? I think that was a question that I think Jim probably answered in most detail. So Jim, if you want to just quickly give a summary answer to that question again.
Yes, yeah, sure. I put an answer into Slido, but I think it was maybe archived. I'm not sure exactly what happened.
Yeah.
So there are two ways that you can initialize any climate model. One is through an observational product called reanalysis. And the second is just from a previous E3SM simulation that provides output. So for the reanalysis is essentially a very fine resolution forecast model that is supplemented by observations such as satellite data, aircraft data, weather balloons, or these sort of drones that are dispersed into the ocean and provide data. And these observations are provided about every 6 hours. And then we use the forecast model to sort of fill in the gaps from these observations. And then all that is gridded on a global grid. And then that is what is used to initialize E3SM.
Yeah, and thank you, Jim. So the next question was, one of the reasons mentioned for the analysis being performed in situ is the IO bottleneck. Does this mean that the raw data is not stored anywhere at all? Is it recorded, consumed by the prediction model, and then discarded? So I'll just quickly say the answer is roughly yes. That's the goal of doing in situ, that you don't have to store the highest resolution data in disk, just because you just cannot store the highest resolution data on disk because it's just too big. And if you want to really move all of the data, then you have to wait for the general things that we already have heard about in situ over like past years or so. So in a nutshell, the answer is yes. But for our particular scenario, if we were just discarding the data or not, as I was writing in my reply, so I think we were still storing some part of the data because the data was not really so big that we could not store anything. So Shomo, do you want to just add a quick answer to that, like particular to our scenario?
Yeah, so we stored the data only for the purpose of comparing our results and validating the model. Otherwise, in the real scenario, when we are confident enough, then even if you try, you wouldn't be able to store it at the highest possible resolution. So you have to sort of throw away the data and then keep the models and depend on them to perform analysis.
Okay. Yeah, thanks, Shomo. And the third question was regarding the initialization using reanalysis. When doing so, do we run the risk of errors from previous simulations being accumulated over time, especially when we don't have supplementary actual measurements to correct those answers? So I think Jim already answered on Slido saying that, every 6 hours or so, we do get like observed data. So in a way, we are doing this automatic or every 6 hours error correction and all. But Jim, if you want to just elaborate slightly on that.
Yeah, so the reanalysis product is the best available data that we have. The second thing is it is supplemented, or observations are assimilated into that forecast model about every 6 hours or so. And the coverage of observations has grown considerably over the past 10 or 20 years due to satellite data and ocean, in situ ocean measurements. And the third thing is that, yes, there are initialization errors, but they tend to fade out relatively quickly. I think usually within about a week or two. And then after that, the model, the errors, the biases associated with like the E3SM physics take over. And so the initialization doesn't really matter if you just allow the simulation to run out, about a week or more.
All right, so I think those were the questions on Slido. So Divya, now we can take it over and see if there are questions in the audience or not.
Okay, thanks, Ian.
Yeah.
Any questions here? Yes. Oh, yeah, it might need to speak up or Oh, thank you.
Yep. Yeah, thanks for the talks and the nice presentations. First, I have a question to Rupsa. So she showed, or you showed a lot of comparisons of observations and simulations with two pictures beneath. And I noticed that in several cases, there were completely different color scales on it. And I think, yeah, was there an intention to do that? So typically, this could be misleading, I would say.
Yeah, Rupsha, do you want to?
Yeah, thank you for the question. So yeah, so some of the plots where I show the difference, the comparison between model and observation, I mentioned that the scales are different, and it mainly because the cyclone statistics is itself different between the model and comparison. So to best represent each of the results, we just keep the scales different. So yes, so we keep the scales intentionally different, and I mention it into the slides. But yeah, it's like a good point. So in the future, we are going to we can tweak the scales to make the results more robust for comparison.
Okay, thanks. And if I I would pose another question maybe to you.
Yes.
So the machine learning application in this case, to my understanding, was used to artificially generate a kind of ensemble information at each location, right?
Yes. So we were basically fitting Gaussian processes to regions of the data.
And how can you be sure that if this works for the current climate correctly, that for future climate, this would be the same? Because, for example, if you look at the maximum temperatures of heat waves, we have seen that heat waves can be much stronger. So is this taken care of by the machine learning mechanism in this case?
Yes, that's definitely something that we're looking at to try to see how much of a prediction we can do to future data. This is kind of the first step to try to see if we can do this at all and try to fit something in situ. But yeah, we have been, future work that we've been working on since we've finished this project have been to see how much can we predict temporally down the line, to see how much we can understand down the line. This is, I think, just a general question that we all want to know. You know, how good of a model do we have that we can construct that we can predict unpredictable things down the line? So it's still a work in progress. You know, as we learn more and more about this, we see that we can predict some things down the line, but of course there's some things that aren't quite captured, and we're trying to see what we can do about that.
Okay, thank you.
Thanks.
So there is one more question on Slido that is about the data sets. So maybe I'll direct this to Jim. The question is recommendations for data sets that a visualization team could use for design and prototyping. So, and I would, like, in a short way, I would say, like, probably the person who was asking, they're talking about where to find the data so that, like, someone can download the data and do analysis. So I can put the link of the E3SM website, but Jim, if you have a more detailed answer while I'm pasting on Slido, please go ahead.
Yeah, so I guess it depends on what kind of data you are interested in. There's the Coupled Model Intercomparison Project, or CMIP. And that's a number of modeling institutions run climate simulations. They're typically at like 100-kilometer resolution, so they're not very fine scale. But all of that data is publicly available, I believe, through the Earth System Grid Federation, ESGF. And there's also the data is hosted on PCMDI, I believe it is. If I don't know, so in any case, those simulations are publicly available, but they're not to the resolution that we're showing here, just because there's not enough storage and bandwidth for data transfer. If someone follows up with me, either Ian, if you want to contact Ian or whoever, I can look it up and get you that information.
Yeah, actually, there is another interesting question that I was sort of expecting that came towards the last. So now the question is, does this panel feel that there are visualization challenges in your work? I think this is an excellent question for the conference and the mode of the conference. So anyone would like to say anything? Like, I can say a few things, but I would just say maybe Shomo, since you have done a few things like in situ where you were sort of visualizing as well as doing data analysis. So what do you feel like from a visualization perspective? You see any challenges? And then I would open this up to Jim, because Jim, you might be able to say what kind of, Jim and Rupsha, you being more of like domain scientist here, what kind of visualization challenges you face. But maybe we can start with Shomo.
Yeah, I mean, I would say that since, as Ayan is saying, that from domain expert, the perspective would be different. But from our point of view, the atmosphere data we had were initially like set of points, right? So it's not like a regular grid data. So you have to do something so that you are able to produce surface representation of the data to show. And the second thing is we are building models. So we are kind of converting the data into some abstract representation, right? Say a set of parameters. So you have to have an idea of what you want to reproduce from the model and then how you want to show it so that you can convey the information. Essentially, suppose some uncertainty quantification matrix that you have computed from the model, or some expected mean temperature value. So those are the quantities which are kind of getting inferred from the model, and then we want to show them. So those we had to think about a little bit. Even though we did not end up using too much sophisticated visualization, but still going from model to going back to the visual space, that is something was challenging, and we had to make sure that we are showing the quantities in a meaningful way.
Yeah. Yeah, thanks, Shomo. So Jim, Rupsha, do you have any comments on what kind of either existing or you see in the future, what kind of visualization related challenges might be coming our way?
I guess I can go first. Yeah, I think just the amount of data is problematic, especially because for computational efficiency, sometimes we run climate simulations on a grid that is not like latitude, longitude, and then you have to remap it to a regular lat-long grid and then do the visualization. That's one aspect. The second aspect is just the pure amount of data in the processing time. But recently I've found out that there are some visualization experts at Los Alamos that will work with scientists to produce simulations that could be made publicly available.
Rupsha, if you're talking, you are muted.
Sorry. So to answer this question, I can actually point out two main aspects. One is, like Jim said, because the data is, so we need some post-processing of the data, because most of the data that I used, they are in a native grid, and to do any kind of feature detection or to do any kind of visualization, I need to convert the data into a lat-long grid. And because of the high resolution nature of the data, those post-processing can take time. And also, second is, when we are visualizing the data, the timing is also a very big aspect, and it's because the amount of data and the resolution of the data. I think the big challenge is related to the time, that it just takes a lot of time to like do any kind of analysis or to represent the data compared to the normal set of data. So yeah, these are the two challenges that exist.
Okay, thank you, Rupsha. So it's 15 minutes past our spotlight time, so I'm going to cut things off now. I want to give everyone here their break. So thank you, everyone, for attending this spotlight. Thank you to all the speakers for presenting your work. And I guess we can leave it at that.
Thank you, Divya, for organizing this.
Yep. Thank you.
Yeah,
Thanks.
thank you.
Thanks.
Have a good rest of the IEEE Viz. Bye, everyone.
Bye bye.
Bye.